Hi folks, it's Mrs. Schaus. We're ready to take a look at some items in section 2.1. We're finally on to chapter 2. We're going to be looking at functions, and in thinking about functions we want to consider their domain and range, both graphically and algebraically. We want to be able to evaluate some functions, again algebraically and graphically, and that's going to include some piecewise functions. Okay. We're also going to take a look at evaluating some different expressions, including something new called the difference quotient that you'll use when you get to calculus. All right, so let's start out here by taking a look at the definition of function. So remember that a relation where each input has exactly one output is the definition for function. Many of the things we're going to do here will feel review, but it is pre-calculus, so sometimes we'll be extending what we know a bit. All right, our domain is the set of all input values, and our range the set of all outputs. I want to make sure that you guys understand that when we're talking about an input variable and an output variable, the terminology that we would typically use would be the independent variable for the x, or whatever variable that we're using as the input, and the dependent variable would be the y. I've rewritten a statement here. Consider G of M equals P. And the reason I use different notation here is I want you to think about the input and output variables, or the independent and dependent variables. In this particular case, M would be our input, so our independent variable. And what we get out here, P, would be the dependent variable. All right, let's take a look at some domain and range items. So for these first couple, they ask us to think about the domain and the range of each function. Well, we've been talking a little bit about radicals, so I hope that you guys understand when you're looking at this and you're thinking about domain, that what sits inside here, the x plus 3, has to be non-negative, so greater than or equal to 0. And if we solve that, x would have to be greater than or equal to negative 3. So if I were going to state the domain, I would say that the domain equals the set of x's, where x is a real number, and greater than or equal to negative 3. There's my domain. How about the range? Well, I want you folks to consider this. If we were trying to keep what's underneath here from being non-negative, that means it would have to be 0 or positive. If I put in the negative 3 here exactly, that would give me my output of 0. But anything else that I put in here that's bigger than negative 3 is going to give me a positive output. So all of the outputs, or y values, are going to be things that are 0 or larger. So I would say the range equals the set of all y's such that y is a real number and the y's have to be greater than or equal to 0. Now there really wasn't a calculation involved in this one. It was more of just kind of analyzing, right? Let's take a look at the next piece here. G of x equals 1 over 2x minus 4. If I'm thinking about the domain, I want to say that what sits in a denominator cannot equal 0. I'll add 4 to each side and divide by 2. Oops. And I'm going to say that x cannot equal positive 2. Yeah, you can see it. If I put a 2 in here, 2 times 2 would give me 4. 4 minus 4 would create division by 0. So again, I'm going to state the domain by saying it's x's that are real numbers but not equal to 2. How about the range? Once we start taking a look at different families of functions, you'll probably have a better feel for this range. So for now, I just want you to think about the fact that I can put any number in here in place of x aside from 2, which is what would create the division by 0. So if I can put in very small numbers or very large numbers, this denominator can really be anything other than the fact that it could be 0. So if it is a very large number, that means 1 over a large number would be really close to 0 itself. If I were to put in a very, very small number, make this denominator something that's, maybe like fractional, you have to invert and multiply because this bar implies division, I could create an output that's very, very large. The only thing that I can't create is a value of 0 itself. 1 over any non-zero number will never be 0. So I want to say that my range is, again, all y's that are elements of the reals but I just can't have a y value that's equal to 0. Notice in this next problem, I ask you to find just the domain and not worry about the range for now, because again, we'll worry about range more when we start looking at families of functions, in particular when we start looking at some of them graphically. All right, in thinking about the domain, since there are no radical pieces to deal with, my only concern is what makes the denominator equal to 0. So I'm going to begin by factoring the denominator. See, that factors into x minus 2, x plus 1. And so each one of these would create a problem if it were equal to 0. So I'm going to say each of these is not equal to 0. And if I isolate the x, that means x cannot equal 2, and x also cannot equal negative 1. So the domain would be all real numbers except for 2 and negative 1. All right, let's think about finding the domain and range of functions that are given graphically. So when I look at this first function and I'm thinking about domain, remember that the domain are all x values. Well, when I look at the x values and I think about, I don't see anything sort of, graphed over in this region, but this is a parabola, so perhaps it should have been graphed this way, but there should be arrows on the ends here. And a parabola will continue to work, if it's working upward, will continue to work to the left and also to the right. So I really can't see the entire graph here. There's no way to draw it so that you can see the entire graph, but x could be any real number with no additional restriction there, because again, we could work as far to the left or to the right if these pieces were to continue working upward. How about the range? Well, those are all the y values. When I look at the piece of the parabola that's given here, it is going to continue upward, but is it ever going to drop down below the x-axis? And the answer is no. Well, if this point sits truly on the x-axis, that means the y value is 0, right? The y value is 0 here, and the y's work up as we work upward. That makes sense, and they're negative as we work downward. So we're going to say that this is all y's that are greater than or equal to 0. Can't have any negative y's. All right, let's move on to the next one. So I've got this function again that really should have arrows on the end. It is still continuing to work upward. As it works upward, it also works out. Even though it is climbing very quickly, it will still work to the right and to the left. So once again, we're going to say that our domain is the set of all real numbers. X can be anything. How about the y's? Well, once again, in a y sense, the values are getting larger as we work up this way, smaller as we work down this way, but they're only allowed to go, down to this line right here, which is where the y is negative 1. So I'm going to say our range is the set of all y's, whoops, supposed to be a y, where y is greater than or equal to negative 1. And we've got one more domain and range problem to look at, and here we've got a piecewise function. I know you've studied piecewise functions before in Algebra 2. The idea is that this is still a function. It does still have graphically the nature of passing the vertical line test. Sorry about the lights there. You'd have to pay attention to that here with the vertical line test, that it is only hitting just the 1 point here, and similarly here, only hitting the 1 point here, because these hollow pieces are not actually included as a part of the function itself. All right, so let's take a look again at the domain, and I want to think about all of the different x's here. And as I look, probably should have an arrow on the end as well. As I look here, the x values certainly would continue on in a negative direction. I don't see sort of any missing x values. X can even equal 0 right here with an output of 1. And again, more x values as we work in a positive direction. It is defined here at 3 because this piece is filled in. And then as I continue on to the right, I see values of 3.5 and 4 and 5 and so on. And again, it's continuing because of that arrow. So once again, x can be any real number. How about the outputs, the range here? All right, well, again, if I think about y is getting smaller and smaller as I work downward, this arrow does imply that I'm not only working to the right, but that I am working down. However, there is a line right here where I see a hollow dot both here and here, which tells me that the function doesn't have an output at this point, which is at -2. So y does not equal -2. Are there any other values? So as we work upward and we're looking at y's that are now 0 and working into the positives, are there any values for which that function doesn't have an output, doesn't have a y value? And the answer is no. So our only missing sort of output, if you will, is the number -2. Okay, so that's a piece with domain. Let's also take a look now at evaluating our functions. And I'm going to start with some evaluating graphically. Remember that what sits here is the input. So this is read f of 0. We want to know the function's value when we use 0 as an input. So if the input, or the x, is 0, all we have to do is read up, and it looks like we're at, well, this isn't maybe the greatest of graphs. It looks like we're at about 1.5, and I think we could approximate that to be 1.5. Any ones I give you on an assessment will be definitely clear. All right, how about f of 2? So if I use an input of 2, that means I'm sitting right here. What's the output, or the y value? Well, I'm right on the x-axis, so that is where the output, or the y, is 0. F of 4, I'm going to write that we can't tell. We can't tell from this particular graph. We do know that it's defined, and if we had it, the equation for the function, we would be able to input a value of 4 and find that output, or we would need to see a larger piece of the graph. How about f of -1? When our input is -1, I'm back here again on the x-axis, so once again the y value, or the output, is 0. Here's another one that, once again, is a piecewise function. It's the same piecewise function that we looked at a moment ago, but now, rather than talking about domain and range, we're evaluating it. For f of -4, that means when the input is -4, we would like to see what the output is, or the y value. At -4, this function has a y value of +4. F of 0. That means that our x value is 0. Now, it almost appears as though there are 2 points. Something's going on here and something's going on here. Well, for this piece, we are getting close to this value, but notice it's a hollow dot, which means that we do not include it. So when the x is 0, our output is actually this point right here, which is where y equals, or the output will equal, 1. F of 3. Again, using 1, 2, 3, here is our x value. We want to know what the y, or the output, is. That's +1 also. And finally, f of 4. If I go over to 4, I'm going to read down 1, 2, 3. It looks like we are at -3. So evaluating graphically really isn't too tough of a skill, and this should really feel like review. How about evaluating when we are given the equation for the function? So here's our given function, f of x equals 5x cubed minus 4x squared. They would like us to find f of -2. Remember, that means that this is going in place of x everywhere that we see it listed in the equation, or the function. So let me go ahead and replace the x here with -2, and we're cubing there. And again, the x here with -2, and we're going to square there. And now we just have some algebraic cleanup to take care of. So if we do -2 cubed, let's see, -2 times -2 is 4, times another -2, that's -8. And here, -2 squared would give us a +4. Still continuing on with that cleanup, this would give me a product of -40, and then minus 16 more. I'm running out of space, so I'll just work over here to the right. -40 minus 16 more is -56. All right, and let's evaluate f of 1. Once again, wherever I see the x, I'm going to put 1 in its place. Since 1 cubed is just 1, and also 1 squared is just 1, this becomes 5 minus 4, or 1 overall. Again, pretty simple, probably feeling quite comfortable with this content, I hope. Let's think about evaluating an expression. And again, I would think for something pretty simple like this, or maybe even this one, you've probably seen it before, will trickle into that difference quotient piece that I know is going to be new to you folks. All right, when you're asked to evaluate f of a, again, remember that whatever sits here in this parenthesis means we're using that as the input in place of the variable. So all I have to do is make the substitution. There's nothing else that I can do to, sort of evaluate or clean this up, simplify in any way. I'm done. Take a look at what sits down below. Again, begin just by making the substitution everywhere we see x. But now in this case, there is some cleanup that we can do. I'm going to begin by squaring this binomial. Some of you might even want to write it, maybe even off to the side here. You've got a plus h times another a plus h, and you'll think about distributing. Some of you call that FOILing. When I do that, I will be left with a squared plus 2ah plus h squared. And to continue with my cleanup, I'm going to distribute the negative sign through. The 3 needs to be distributed through all the way here. And now I'm just going to look for any like terms to combine. I've got an a squared term, no other a squared. An ah term, I don't see any. H squared, nope. A linear a term or h term, nope. So in fact, in this particular case, there are no other like terms for me to combine, and that's as simple as it's going to get. Okay, let's take a look now at this piece that I'm calling the difference quotient. They're giving us this function, which is the same function that we were working with just a moment ago, but now they want us to evaluate the function at f of a plus h minus f of a, and take that entire numerator and we're going to divide by h. It does say note that this is called a difference quotient. You might not know its intended purpose at this point, but you will use it when you get to calculus. So for now, our job is just to become more proficient at being able to evaluate the expression. All right, let's take a look. Remember that whatever sits here is going to go in place of x. So I'm just going to rewrite this part of the expression as 3 times a plus h squared minus a plus h plus 2. That right there, this piece is all of f of a plus h. But now from that, maybe I'll put it in a bracket here, from that I need to subtract off f of a. And f of a takes this entire expression and puts a everywhere that I see. Whoops, the x. I'm going to make that a bracket. And the whole thing is divided by h. So now what I have is a whole lot of cleanup to do. Again, I'm going to begin by taking this binomial and squaring it. So it becomes a squared plus 2ah plus h squared. I'm going to distribute the negative sign through, so minus a minus h plus 2. And then this entire quantity is being subtracted, so it becomes minus 3a squared plus a minus 2, and the whole thing is all over h. Next, we need to distribute the 3 through. So I've got 3a squared plus 6ah plus 3h squared minus a minus h plus 2 minus 3a squared plus a minus 2 all over h. Let's continue on with our cleanup here. We want to think about combining some like terms. When I look at this first term, 3a squared, what I notice is that down here, there's also a minus 3a squared. How about other terms that we see that we can combine? I see a negative a and a positive a. I see a positive 2 and a negative 2. I'd combine those if I could, but hey, they end up being opposites of one another, so they cancel from the expression. What am I left with? I've got a 6ah plus 3h squared minus h, and that whole thing is divided by h. Now some of you might think, let's stop there. But I'm going to move over here to the right. I want you to notice that each of the remaining terms has h in it as a factor. And so I can factor h out of each of those terms. And now once I've done that, I can cancel the factor of h here with the one that sits down below, and the entire expression becomes 6a plus 3h minus 1. Okay, we're going to take a look at one more of that style. We're given a different function this time, f of x equals 2x over x minus 1, and we're still evaluating this difference quotient. I'm thinking I might need more room, so I'm going to try to make almost a little bit of a column here and then come over here and make another column if needed. Let's begin by evaluating f of a plus h. That means that I'm going to take this function, and where I see the x, I'm putting a plus h in its place. So this piece represents just f of a plus h. Let's subtract away from that f of a, which is subtracting 2a over a minus 1. And that is all over h. Let's see what that equals. Well, up top here I've got 2a plus h over a plus h minus 1. Maybe I'd like to distribute here. Let me go back and distribute. There we go. All right. And the rest I'm just rewriting. Now, in order to be able to do this subtraction, you guys know we have to have a common denominator. So that means that I need a factor of a plus h minus 1 and a factor of a minus 1. This first fraction will need to be multiplied by a minus 1 on the top and on the bottom. This second fraction will need to be multiplied by a plus h minus 1. And again, it's on the top and on the bottom. And that is all over h. All right, now I've got some work to do. I've got to actually multiply together here and distribute not just the 2a, but the negative 2a through each of these terms. And because I've got the common denominator, once I do that subtraction, I'll keep my common denominator. So let me move up over here for space sake. That leaves me with 2a squared minus 2a plus 2ah minus 2h. And then now again, if I distribute here, the minus sign coming along with the 2a, I get minus 2a squared minus 2ah and then plus 2a. That is all over a plus h minus 1 times a minus 1, the common denominator, and that is all over h. Now I think at this point, instead of writing all over h, I'm going to change this division to being multiplied by the reciprocal here, which would be times 1 over h. Let's see what that equals now. When I look to clean up the numerator here, once again I notice I've got a minus 2ah, or I'm sorry, a plus 2ah, and over here a minus 2, I said 2ah. Let me try again. A 2a squared and a minus 2a squared. I've got minus 2a and a plus 2a. I've got a positive 2ah and a negative 2ah. And the only thing left in the numerator now is negative 2h over a plus h minus 1 times a minus 1, and that is being multiplied by 1 over h, which means that I also have now another factor of h just sitting in the denominator here. Notice that of the terms left in the numerator, which is only 1, right? We've only got one term left in the numerator. It does have a factor of h. So I can cancel that factor of h with the factor of h that I have down in the denominator, and the whole expression is now simplified to be minus 2 over a plus h minus 1 times a minus 1. If you'd like to, you could expand this part out, but I don't really think that it's necessary for us to do that at this point, so I'm going to go ahead and leave it. What is important to me is that we're able to get rid of this h. If you look back at the last example and this example, you know what happens is essentially that we're able to get rid of that piece. Okay, let's look at evaluating piecewise functions. We did some evaluating already, but graphically we took a look at the piecewise function, but we didn't take a look at it in an algebraic sense, so I wanted to come back to that. So here's our function, f of x equals, and essentially there are three pieces that are described. F of x equals 2x if our x's are less than 0. F of x equals x plus 2 if our x's are greater than or equal to 0 but less than 2. And our function equals x squared if x is something greater than or equal to 2. When you're thinking about evaluating, now you have to ask yourself, am I using this first description, the middle one, or the bottom one? And that's determined by the domain. You know, sort of where this falls within the domain. So if I'm using -1 as an input, that is something that is less than 0. So that means I'm going to use this top piece. My function, f of x, is going to equal 2x for that piece. So I just evaluate 2 times my x value of -1, which gives me -2 as an output. Okay, how about finding f of 2? So I look up here, is my x less than 0? No. Look at the next piece. Is it greater than or equal to 0 but less than 2? No, it's not less than 2. It's actually right equal to 2, right? And so I use the third piece. My x is greater than or equal to 2. So I'm using f of x equals x squared, which means I've got 2 squared or 4 as an output there. And for the very last one here, f of 4, once again, I look at these three pieces to decide what, which part of the domain that I'm considering for my input. It is an x that's greater than or equal to 2. So once again, I'll use the same piece, f of x equals x squared, with an input of 4. 4 squared gives me an output of 16. Okay. So you guys, you know the drill. You're going to do some exercises from section 2.1, focusing on a variety of these types of skills, and we'll work together some more in class. Reach out to me with questions, folks, and make it a great day. Talk to you soon.